Look up at the night sky on a clear evening. You see stars, planets, the vast emptiness of space. But what if I told you that emptiness is an illusion? What if the very fabric of our universe is imprinted with the ghostly afterglow of creation itself? This is the cosmic microwave background, the oldest light in existence, a baby picture of the cosmos taken when it was just 380,000 years old. For decades, scientists have mapped this faint glow, charting the subtle variations in temperature that tell the story of how everything we know began. It's a map of our cosmic origins, and for the most part, it looks exactly as our best theories predict. But then there is the anomaly. Tucked away in the constellation Eridanus, there is a place that defies explanation. A vast, chilling void in the cosmic warmth, a region so cold and so empty that it has sparked one of the most daring questions in modern physics. Is this mysterious cold spot simply a cosmic flaw, a statistical glitch in the data, or could it be something far more profound, something that hints at a reality beyond our own? Could it be evidence of a collision with a parallel universe? This isn't science fiction. This is the frontier of cosmology, a genuine puzzle that challenges our fundamental understanding of reality. The cold spot is enormous, 1 billion light-years across of nothingness. It's colder than it should be, a cosmic desert on a scale that is difficult to even comprehend. When it was first discovered, the simplest explanation was that it was just a giant supervoid, an immense region of space with far fewer galaxies than average. But even that extraordinary idea falls short. The scale is simply too vast, the coldness too extreme. The numbers don't add up. This leaves scientists with a breathtaking, almost unbelievable alternative. What if this cold patch is a cosmic bruise? A scar left on our universe from a traumatic impact with another universe, a separate bubble of reality in the multiverse. Today, we are going on a journey to the very edge of known physics. We will dive into the data, explore the competing theories, and confront the mind-bending possibility that our universe is not alone. We'll start with the meticulous science behind the cosmic microwave background and build to the thrilling speculation of a multiverse collision. This is a story about human curiosity pushing against the limits of knowledge, about looking into the deepest map of reality and finding something that whispers of other worlds. So get ready, because we are about to explore one of the greatest mysteries of the cosmos. A mystery that might just change everything we think we know about existence. To understand why this cold spot is so baffling, we first need to appreciate the canvas on which it appears. That canvas is the cosmic microwave background, or CMB. Think of it not just as light, but as the very first breath the universe took after it was born. For the first few 100,000 years of its existence, the cosmos was a searing, opaque fog of plasma, so dense that light particles, photons, couldn't travel anywhere without immediately crashing into something. The universe was a brilliant, blinding blaze. Then, in a pivotal moment known as recombination, the universe expanded and cooled just enough for electrons and protons to combine into neutral atoms. Suddenly, the fog lifted. The photons which had been trapped were finally set free. They began streaming across the universe, and they've been traveling ever since. What we detect today as the CMB is that very first flash of light, now stretched and cooled by the expansion of space over billions of years into a faint whisper of microwave radiation. It is quite literally the oldest thing we can ever see, a fossil from the dawn of time. The story of its discovery is a classic tale of scientific serendipity. In the mid-1960s, two radio astronomers named Arno Penzias and Robert Wilson were working with a massive, extremely sensitive horn antenna in New Jersey. They were trying to eliminate a persistent, annoying hiss of background noise that was interfering with their satellite communications research. They pointed the antenna everywhere in the sky, but the noise was always there, day and night. They even famously cleaned out a nest of pigeons that had been roosting in the antenna, suspecting their droppings, which they referred to as a white dielectric material, might be causing the interference. But even after a thorough cleaning, the hiss remained. It was a universal, constant signal coming from all directions. What they had accidentally stumbled upon was not a technical flaw, but the echo of the Big Bang itself. That faint, uniform hiss was the cooled remnant of the universe's fiery birth. For this incredible, accidental discovery, they were awarded the Nobel Prize in Physics in 1978. What makes the CMB so powerful for cosmologists is its incredible uniformity. After its 13.8 billion-year journey, that primordial light has cooled to a frigid 2.7 degrees above absolute zero. And no matter where you look in the sky, the temperature is almost exactly the same. Those tiny, tiny fluctuations in temperature on the order of 1/100,000th of a degree are not imperfections. They are the seeds of all cosmic structure. They represent the slight variations in density in the early universe, the gravitational blueprints that would eventually, over eons, collapse to form the first galaxies, stars, and everything we see today. Because this background is so remarkably even, it acts as a perfect control. It's the baseline against which we measure the cosmos. So when we find a region that deviates significantly from this baseline, like the cold spot in Eridanus, it's not just a curiosity. It's a glaring red flag, a signal that something extraordinary happened, either during the universe's infancy or sometime after, to create such a profound departure from the expected order. It's like looking at a perfectly smooth sheet of ice and finding one single, massive, and inexplicable crack. Yet for all its power, the Wilkinson microwave anisotropy probe was designed to measure the subtle, not the spectacular. Its mission was to refine our picture of the early universe by charting those tiny temperature variations with unprecedented precision. And for the most part, that's exactly what it did, providing a stunningly detailed map that largely confirmed our standard model of cosmology. But when a team of astronomers led by Dr. Lawrence Rudnick from the University of Minnesota began sifting through this new, high-fidelity data in 2004, they found something that stood out like a cosmic sore thumb. It was a region in the southern constellation Eridanus that was significantly, inexplicably colder than the rest of the sky. This wasn't one of the expected small-scale ripples. This was a vast, deep chill, a colossal anomaly on the map. The temperature drop was measured at around 70 microkelvin colder than the average background. Now, that number might sound incredibly small, but in the context of the CMB's incredible uniformity, a fluctuation of that magnitude across such a huge area is statistically monumental. It's the difference between a calm sea with normal waves and a sea with a single, impossibly deep and wide trench. The sheer scale of the cold spot is what truly boggles the mind. It spans an area of the sky about 5 degrees across. To put that in perspective, hold your fist out at arm's length. It covers roughly 10 times that area. In terms of actual physical size, based on our understanding of cosmic distances, this translates to a void potentially 1 billion light-years in diameter. We are talking about an emptiness so vast it could contain tens of thousands of galaxies, yet it appears to contain far, far fewer than it should. This was the core of the mystery that Rudnick and his team unveiled. It wasn't just a cold patch, it was a profound absence, a great cosmic nothing that challenged our understanding of how the universe structures itself on the largest scales. The discovery immediately set off a race for an explanation, a scientific detective story that would lead from the straightforward to the truly surreal. The first reaction in any scientific discovery, especially one this strange, is a healthy dose of skepticism. Could this cold spot be a mistake, a digital ghost in the machine, an artifact created by the very instruments we use to observe the cosmos? After all, the Wilkinson microwave anisotropy probe was a marvel of engineering, but it was not infallible. Every complex instrument has its quirks, its potential sources of error. Scientists had to be absolutely certain they were looking at a feature of the universe itself, and not just a flaw in their own map. This process of rigorous self-checking is the bedrock of modern science. It's what separates a genuine discovery from a simple anomaly. So, the international community of cosmologists turned their attention and their most powerful tools toward the constellation Eridanus to put the cold spot to the test. The definitive answer came from a successor mission, a spacecraft even more advanced than its predecessor, the Planck satellite. Launched by the European Space Agency in 2009, Planck was equipped with instruments of unprecedented sensitivity, designed to map the cosmic microwave background with a resolution and accuracy that would make the earlier maps look like a rough sketch. If the cold spot was real, Planck would see it with crystal clarity. If it was an error, it would vanish like a mirage under this sharper gaze. When the Planck team released their high-definition map of the entire sky, the scientific world held its breath. There it was, unmistakably present, etched into the data with even greater detail. The cold spot had passed the ultimate test. It was confirmed as a real feature of our universe, a tangible and significant structure imprinted on the oldest light we can see. This confirmation was a pivotal moment. It transformed the cold spot from an intriguing maybe into a concrete scientific problem, a phenomenon that our current models of the universe now had to explain. With the possibility of an instrument error firmly ruled out, the search for a physical explanation within our universe began in earnest. The most logical and straightforward hypothesis was that the cold spot is a supervoid. Imagine the large-scale structure of the universe as a cosmic web, a vast network of galaxy clusters and filaments surrounding enormous, empty bubbles. A supervoid is simply an exceptionally large one of these bubbles, a region of space with a significantly lower density of matter than the surrounding areas. The connection to temperature comes from a subtle but powerful effect in cosmology known as the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels across the universe for billions of years, it climbs in and out of the gravitational wells created by matter. When light enters a gravitational well, it gains energy, making it appear slightly hotter. When it climbs out, it loses energy, appearing slightly cooler. Normally, in a static universe, these effects would cancel each other out. But because our universe is expanding at an accelerating rate, the gravitational wells themselves are weakening over time. This creates a subtle imbalance. As a CMB photon passes through a large, matter-rich region, the well it climbs out of is shallower than the one it entered. This means it loses a little more energy than it gained, resulting in a net cooling effect. So, if the cold spot is indeed a giant supervoid, the light passing through it would lose more energy, making that region of the CMB appear colder. It's a perfectly sound, well-understood physical mechanism. The problem is, the numbers just don't add up. So the supervoid hypothesis became the leading candidate, the most conventional and scientifically grounded explanation for this cosmic mystery. Imagine our universe on the largest scales, not as a uniform soup, but as a magnificent cosmic web. Vast filaments of dark matter, sparkling with galaxies, weave through the emptiness, connecting at dense nodes where enormous galaxy clusters reside. And between these brilliant strands lie the void's immense, dark, and mostly empty bubbles. A typical void might be tens of millions of light years across. But the structure proposed to explain the cold spot would have to be something far grander, a supervoid. This would be a region of space of almost unimaginable scale, 1 billion light years in diameter, that is profoundly underdense. Where a typical volume of space might contain thousands of galaxies, this supervoid would hold only a handful, a cosmic desert of staggering proportions. The mechanism linking this emptiness to a cold spot is a subtle but powerful cosmological effect, one that ties directly into the accelerating expansion of our universe. It's called the integrated Sachs-Wolf effect, To understand it, picture a photon from the cosmic microwave background beginning its 13.8 billion-year journey toward us. As it travels, it passes through regions of varying gravitational pull. When the photon flies into a region with lots of matter, a galaxy cluster for instance, it must climb down into that gravitational well. This process actually gives the photon a tiny boost of energy, making it appear very slightly warmer. Later, as the photon climbs back out of the well, it loses that energy, cooling back down. In a universe that wasn't accelerating, these gains and losses would perfectly cancel each other out over the long journey. But our universe is not static. It's expanding at an ever-increasing rate due to dark energy. This acceleration changes the game. The gravitational wells that the photon encounters are not frozen in time. They are slowly being stretched out and weakened by the expansion of space itself. So, when a photon enters a dense region, it gains a certain amount of energy, but by the time it leaves, millions of years later, the gravitational well has become shallower. The photon doesn't have to work as hard to climb out, meaning it loses less energy than it gained on the way in. The result is a net gain, a very slight warming of the symbiphoton. Now consider the flip side. When a photon passes through a giant void, a region with much less matter, the opposite happens. There is no deep well to climb into, so it gains very little energy on entry. But as it travels through the void, the expansion of space is actually causing the void itself to become even emptier, creating a subtle gravitational hill. To climb out of this expanding underdensity, the photon must expend energy. It loses more energy escaping the void than it gained entering it, resulting in a net energy loss. This manifests as a cooling effect. For a void of the proposed scale, the cumulative cooling could, in theory, account for the temperature drop we see in the cold spot. It's an elegant solution, a direct consequence of well-established physics involving gravity and cosmic acceleration. For a time, it seemed like the mystery was solved. Astronomers began searching for this predicted supervoid, scanning the region of the cold spot with powerful telescopes, expecting to find a corresponding absence of galaxies. So the hunt was on. Armed with the supervoid hypothesis, astronomers turned their most powerful optical telescopes toward the constellation Eridanus, expecting to map a staggering emptiness. They conducted extensive galaxy surveys, meticulously counting the number of galaxies in the direction of the cold spot and comparing it to other parts of the sky. And indeed, they found something. A large void does exist in that region, but here's where the mystery deepens rather than resolves. The void they discovered is significant, but it's a far cry from the colossal billion-light-year-wide supervoid the theory demanded. The observed underdensity is more on the scale of a few 100 million light-years across. This might still sound enormous, but in cosmological terms, it's simply not big enough or empty enough to pack the gravitational punch required to create the profound cold spot we observe through the integrated Sachs-Wolf effect. The numbers, when crunched, reveal a glaring discrepancy. The actual underdensity of galaxies can only account for perhaps 20% of the observed temperature drop. Where is the other 80% coming from? This is the core of the fine-tuning problem. For the standard supervoid explanation to work, we would need a void of such a specific, immense, and statistically unlikely size and emptiness that it starts to feel contrived. It would be a 1 in a million cosmic coincidence. Science, of course, deals in probabilities, and sometimes rare things happen. But when a straightforward explanation begins to require an ever-increasing list of unlikely conditions, it forces researchers to ask a difficult question. Are we trying to force a square peg into a round hole? Is the universe trying to tell us that the real answer is something we haven't even considered yet? The failure of the supervoid to fully explain the anomaly is what truly flung the doors wide open for more radical and, frankly, more thrilling possibilities. It transformed the cold spot from a potential curiosity of large-scale structure into a genuine crack in the foundation of our standard model of cosmology. This dead end with conventional explanations is precisely what forces us to look beyond the boundaries of our own universe for an answer. When the laws of physics as we understand them cannot account for an observation, it's not necessarily a failure. It can be an invitation to a grander picture. And the picture doesn't get much grander than the multiverse. This idea, once confined to the pages of science fiction, has become a serious, albeit speculative, topic of discussion among cosmologists and theoretical physicists. The multiverse proposes a staggering reality that our universe, with its specific laws, constants, and properties, might not be the only one. Instead, it could be just one bubble in a vast, possibly infinite, cosmic foam of universes, each with its own unique physics. This isn't a single, unified theory, but rather a consequence that pops out of several of our most successful attempts to understand reality. One of the strongest lines of evidence for a multiverse comes from the theory of cosmic inflation. This is the idea that a fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion, smoothing it out and seeding the structures we see today. While inflation explains a great deal, most models suggest that once inflation starts, it's virtually impossible to stop everywhere at once. Think of a pot of boiling water. A bubble of steam forms and expands, but outside that bubble, the water is still boiling and new bubbles are constantly forming. In this analogy, our entire observable universe is just one bubble in an eternally inflating cosmic sea. Each of these bubble universes undergoes its own Big Bang and evolves with its own set of physical laws and constants. The fundamental forces gravity, electromagnetism, the strong and weak nuclear forces could have different strengths in other bubbles. Some universes might expand too quickly for stars to ever form. Others might collapse back in on themselves instantly. We just happen to live in one where the constants are perfectly tuned for galaxies, planets, and life to exist. This is often called the anthropic principle. We shouldn't be surprised to find ourselves in a universe capable of supporting us, even if it is just one rare bubble in a multiverse of inhospitable ones. Another compelling version of the multiverse emerges from the enigmatic world of string theory, a candidate for a theory of everything that attempts to reconcile gravity with quantum mechanics. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. The way these strings vibrate determines the properties of the particles they become. However, for the math to work, string theory requires extra spatial dimensions beyond the three we experience. These dimensions are thought to be compactified, or curled up into shapes so small we can't perceive them. The catch is that there are a staggering number of ways these dimensions can curl up, perhaps 10 to the 500 different ways. Each unique configuration would result in a universe with a different set of physical laws and constants. So, within the framework of string theory, our universe is just one specific solution, one page in a cosmic library of possibility containing more potential universes than there are atoms in our own. This is known as the string theory landscape. While these ideas are highly theoretical and currently untestable through direct experiment, they provide a robust mathematical foundation for the concept of a multiverse, transforming it from pure philosophy into a plausible, if distant, scientific frontier. And it is against this backdrop of a possible multiverse that we arrive at the most dramatic and fascinating explanation for the cold spot. The idea is as simple as it is profound. If our universe is indeed one bubble in a frothing sea of inflating space, what happens when two of these bubbles happen to form too close to each other? In the chaotic environment of eternal inflation, it's not just possible but perhaps even probable that neighboring bubbles would occasionally bump into one another as they expand. Picture two soap bubbles floating in the air, slowly growing. If they touch, they don't usually pop each other instantly. Instead, they can merge, their surfaces flattening against one another at the point of contact. Now transpose that image to a cosmic scale. Our universe and a parallel universe, each a distinct bubble of space-time with its own laws of physics, inflating within a grander meta-universe. If they collided when both were still incredibly young and relatively small, the impact would have sent a shockwave rippling through the very fabric of both realities. This is where the cold spot enters the picture. The theory proposes that this vast, cold region in the cosmic microwave background is the cosmic scar, the lingering imprint of such a collision that occurred before the CMB was even emitted. At the moment of contact, the energy at the boundary would have been immense. The collision would have injected a tremendous amount of energy into the region of our universe at the point of impact. But counterintuitively, this injection of energy could have actually created a cold spot. How? The mechanism involves the subtle interplay between energy and the expansion of space. The sudden influx of energy from the collision would have accelerated the expansion of that specific region of our universe for a very brief period. This faster-than-normal expansion would have stretched the photons of light traveling through that area more than the photons elsewhere. And as light is stretched, it loses energy, shifting to longer, redder wavelengths and becoming cooler. The photons that were destined to become part of the CMB, passing through this bruised region, would have been super-cooled by this event. When the universe finally became transparent and released the CMB, that patch of sky would have been permanently marked as colder than its surroundings. The cold spot in this view is not an absence of something, but the ghostly fingerprint of an encounter with another world. It's a fossilized record of a time when our cosmos was not isolated, but interacted with a separate reality. This hypothesis provides a potential solution to the fine-tuning problem that plagued the supervoid explanation. We wouldn't need an impossibly large and empty void. We would need a physical event that could impart a specific, localized cooling effect on the primordial plasma, which is exactly what a bubble collision could do. The immense scale of the cold spot, 1 billion light-years across, simply reflects the colossal size of the interacting bubbles. While this idea pushes the boundaries of credibility, it is a hypothesis grounded in the mathematics of inflationary cosmology. It's a testament to how far scientists are willing to go to follow the evidence, even if it leads to a conclusion that seems ripped from the pages of a fantasy novel. So, if this breathtaking idea is correct, what would the evidence of such a cataclysmic event actually look like? The answer lies in the unique signature a collision would leave on the cosmic microwave background. Theorists suggest that when two bubble universes make contact, the interaction wouldn't be a chaotic explosion, but a highly structured event governed by the fundamental laws of physics that apply in the space between the bubbles. The key is to think about the boundary where the two universes meet. Each bubble has its own vacuum state, its own lowest possible energy level, like the calm surface of a pond. When they collide, it's as if two different ponds are suddenly connected. The energy fields at their boundaries would interact, creating a complex and energetic region where the rules of both universes are in a kind of cosmic negotiation. This interaction would generate a powerful shockwave, a ripple of energy that propagates outward from the point of impact, traveling through the infant universe at a significant fraction of the speed of light. This is where the soap bubble analogy becomes incredibly useful. Imagine gently pushing two soap bubbles together until their shimmering surfaces just touch. At the point of contact, the film of each bubble flattens against the other, forming a distinct circular boundary. In the cosmic version, the skin of each universe is its space-time fabric. The collision would create a similar circular or disk-like region where the properties of our universe are subtly altered by the influence of its neighbor. This disk would be the epicenter of the event. The immense energy released wouldn't just heat things up. Its primary effect would be to briefly but dramatically accelerate the expansion of space within that specific region. It's like giving that one part of the universe an extra powerful shove. Now, remember those primordial photons that would later become the CMB racing through this rapidly stretching space. As space expands, it stretches the wavelength of light traveling through it. The more rapid the expansion, the more the light is stretched. And when light is stretched to longer wavelengths, it loses energy and cools down. So, the photons that passed through this collision-bruised zone would have been cooled more than the photons traveling through undisturbed space. When the universe finally became transparent, this entire disk would appear as a vast, cold spot on the sky, a perfect circular imprint of the contact point. What's truly remarkable is how well this theoretical signature aligns with the actual cold spot. The observed anomaly isn't just a random, blurry patch of cold. Detailed analyses of its shape suggest a profile that is consistent with a circular feature on the sky. Furthermore, the temperature gradient, how the coldness changes from the center of the spot to its edges, matches what models predict for a bubble collision. The collision wouldn't create a sharp, icy circle, but rather a central region of maximum cooling that gradually fades into the background temperature, much like the ripples from a stone dropped in a pond smooth out as they travel outward. This level of detail is what makes the hypothesis so compelling to some scientists. It's not just a hand waving, maybe it was another universe. It's a specific, falsifiable prediction that can be compared against the data. A random cosmic flaw or an unusually large void wouldn't necessarily produce such a distinct and theoretically predicted pattern. The bubble collision idea, for all its strangeness, provides a concrete physical mechanism that accounts for the cold spot's specific size, shape, and temperature profile in a way that conventional explanations have so far struggled to match. To truly grasp how a collision with another universe could leave a mark on our own, we need to venture into the quantum realm, to the very rules that govern reality at its most fundamental level. The key lies in understanding the nature of the vacuum. In everyday language, a vacuum means empty space, a complete void. But in quantum field theory, vacuum is anything but empty. It's a seething, bubbling sea of potentiality, where virtual particles constantly flicker in and out of existence. This vacuum energy isn't just a theoretical curiosity. It's the engine behind the accelerating expansion of our universe, what we call dark energy. Crucially, different bubble universes in the multiverse could have vastly different vacuum energies. One universe might have a high vacuum energy, causing it to expand at a ferocious rate, while another, like our own, might have a relatively low value, allowing galaxies and life to form. When two such bubbles collide, it's not like two planets smashing together. It's a confrontation between two different, stable states of reality, two different vacuums. The boundary where they meet becomes a domain of incredible tension. Think of it as a cosmic firewall, a region where the quantum fields of our universe interact violently with the alien fields of the intruding universe. This interaction releases an immense amount of energy, but the effect on the primordial plasma of our young cosmos is counterintuitive. You might expect an injection of energy to create a hotspot, but the dominant effect is actually on the expansion rate of space itself within the collision zone. The energy from the collision acts as a temporary, powerful dose of dark energy, causing that specific region of our universe to inflate, to stretch much more rapidly than the space around it. This period of hyper-expansion is the crucial mechanism that imprints the cold spot. Remember the photons that were trapped in the hot plasma soup. As this region of space undergoes its accelerated stretching, the photons within it are stretched along with it. Stretching a light wave means increasing its wavelength, and increasing its wavelength directly corresponds to a loss of energy. In the context of the cosmic microwave background, a loss of energy is observed as a lower temperature. So, the photons that were in the collision zone got an extra dose of cooling because the space they were traveling through was temporarily stretched more than anywhere else. By the time the universe became transparent, these photons were permanently cooler than their counterparts, creating the vast circular cold spot we observe today. One of the most prominent voices championing this extraordinary explanation is theoretical physicist Laura Mersini-Houghton. Her work in the mid-2000s was among the first to make a detailed, testable prediction based on the multiverse hypothesis. She didn't just propose that the cold spot could be a collision. She used the mathematics of quantum mechanics and the landscape of string theory to predict what such a signature should look like in the CMB data. Her calculations suggested that if our universe is part of a multiverse, then the gravitational pull of neighboring universes during its infancy should have left specific imprints on the large-scale structure of the cosmos. Remarkably, when the Wilkinson microwave anisotropy probe data was released, it contained several large-scale anomalies, including the now famous cold spot in Eridanus, that aligned strikingly well with the patterns her models had forecast. For Mersini-Houghton, this wasn't just a coincidence, it was potential empirical evidence for the existence of other universes. Her approach embodies a shift in cosmology, moving the multiverse from a purely philosophical idea to a framework that can make predictions about our observable universe. Of course, her ideas are controversial and far from universally accepted, but they represent a bold attempt to confront one of the biggest mysteries in science with one of the most profound possible answers. She argues that the cold spot, along with other large-scale anomalies, points to a cosmos that is not infinite and isolated, but finite and connected to a larger multiversal structure, with the cold spot serving as a tangible, if ghostly, relic of that connection. But a temperature map is only one piece of the puzzle. To truly put the collision hypothesis to the test, scientists realized they needed to look for a different kind of ghostly imprint, one that would be far more difficult to forge by chance. This leads us to the fascinating property of light known as polarization. We often think of light as a wave that simply moves forward, but it also has an orientation, a direction in which its electric field vibrates. Normally, the light from the cosmic microwave background is unpolarized. Its vibrations are jumbled in all different directions, a chaotic remnant of the hot, dense plasma of the early universe. However, in the final moments before the universe became transparent, that raging sea of particles began to calm down just enough for a subtle ordering to occur. The free electrons, which had been scattering photons in every direction, were finally being captured by protons to form the first atoms. During this last scattering event, the way photons bounced off these electrons imprinted a specific, very faint pattern of polarization on the CMB light. It's a delicate fossilized swirl, a signature of the very last interaction that light had with matter. This primordial polarization comes in two main types. The first, called E-mode polarization, is a relatively gentle, curl-free pattern that is primarily generated by the density fluctuations in the early universe, the same ripples that created the temperature variations. It's a pattern that fits neatly within our standard model of cosmology. The second type, B-mode polarization, is far more elusive and telling. This pattern has a distinctive handedness, a curl to it, like the water swirling down a drain. While some B-modes can be created by gravitational lensing, where the CMB light is bent by the gravitational pull of matter it passes on its long journey, the most sought-after source is something far more dramatic: primordial gravitational waves. These are not the recently detected waves from black hole mergers, but gargantuan ripples in the very fabric of spacetime itself, generated during the violent hyper-expansion of the universe's first instant, the period of inflation. Finding these primordial B-modes would be like discovering the fossilized footsteps of the Big Bang's driving engine. This is where the bubble collision theory makes its boldest and most specific prediction. A collision with a parallel universe would not have been a gentle nudge. It would have been a cataclysmic event, sending powerful shockwaves through the infant cosmos. Such a tremendous release of energy would have violently shaken the fabric of spacetime, generating a localized storm of gravitational waves right at the site of the impact. These waves would have rhythmically squeezed and stretched the primordial plasma as the CMB photons were being set free. This mechanical disturbance would have imparted a unique, swirling B-mode polarization pattern directly onto the cold spot itself. Crucially, this signature would be correlated precisely with the location and shape of the temperature anomaly. It wouldn't be a faint, uniform background signal. It would be a bright, specific bullseye of curled polarization centered on the cold spot. For scientists, this is the smoking gun. If they could find this distinct B-mode pattern exactly where the collision theory says it should be, it would provide compelling, multi-layered evidence that is incredibly difficult to explain by any other means. The hunt for this definitive signature is now underway, pushing the limits of our observational technology. Teams are reanalyzing data from the Planck satellite with sophisticated new algorithms, searching for any hint of a polarized signal within the confines of the cold spot. Meanwhile, a new generation of ground-based telescopes, located in the ultra-dry, high-altitude deserts of the Atacama in Chile and the South Pole, are being deployed. These instruments, like the Simons Observatory and the upcoming CMB-S4 project, are designed with an unprecedented sensitivity to polarization. They are essentially the most powerful polarizing sunglasses ever built, capable of detecting the faintest swirls in the ancient light. The challenge is immense. The predicted signal is exquisitely weak, buried under foreground interference from our own galaxy's dust and the subtle lensing effects of the cosmic web. Distinguishing the hypothetical collision signal from this cosmic noise is a monumental task in data analysis. The absence of this correlated B-mode pattern, however, would not necessarily kill the collision idea outright, but it would place severe constraints on the model, forcing theorists back to the drawing board. The presence of the signal, though, would ignite a scientific revolution, transforming the cold spot from a compelling mystery into our first tangible window into the multiverse. Of course, the search for an explanation doesn't end with the multiverse. While the bubble collision idea captures the imagination, the scientific process demands that we explore every possible avenue, no matter how unconventional. Before we leap entirely outside our cosmic bubble, there are other exotic theories that, while strange, still operate within the confines of a single universe. These ideas push the boundaries of known physics but stop short of invoking parallel realities. They are the cosmic Plan B options, each with its own fascinating implications. One compelling alternative focuses on the universe's greatest mystery, dark matter. We know this invisible substance makes up about 85% of all the matter in the cosmos, its gravitational pull acting as the cosmic scaffolding upon which galaxies are built. But what if the cold spot isn't a void of regular matter, but instead a colossal, concentrated knot of dark matter? Imagine a region of space not empty, but filled with an unimaginably dense cluster of this enigmatic substance. The gravitational effect of such a super-dense dark matter node could be profound. As photons from the cosmic microwave background travel toward us, they must climb out of the gravitational well created by any massive object. This process, known as gravitational redshift, causes the photons to lose energy and thus appear cooler when we finally detect them. A sufficiently massive and concentrated clump of dark matter could, in theory, create a gravitational well deep enough to produce the significant cooling we observe. The challenge with this idea is that our current models of dark matter suggest it is cold and collisionless, meaning it shouldn't naturally clump together into such ultra-dense structures on such a vast scale. Finding one would force a major revision of our understanding of dark matter itself, making it a revolutionary discovery in its own right. Another deeply theoretical possibility involves cosmic defects in the fabric of spacetime itself. In the early universe, as it expanded and cooled, the fundamental forces that govern reality are thought to have undergone phase transitions, much like water freezing into ice. And just as freezing water can create cracks and fissures, these cosmic phase transitions might have created flaws in the structure of spacetime. One such hypothetical flaw is called a texture. A texture isn't an object made of matter. It's a kink or a twist in the very geometry of the universe, a knot of concentrated energy in the quantum fields that define reality. If such a texture existed and a CMB photon passed through it, the sudden change in the spacetime geometry would directly affect the photon's energy. The specific nature of a texture's gravitational field could cause a net loss of energy for the photon, creating a cold spot in the sky. While textures are predicted by some grand unified theories, they remain entirely hypothetical. Detecting one through the cold spot would be a monumental validation of theories that attempt to unify all the forces of nature, offering a glimpse into the physics that operated at energies trillions of times higher than anything we can create in a particle collider. Perhaps the most mind-bending of all the single universe explanations challenges the very notion of a beginning. What if the cold spot is not an artifact of the Big Bang, but a relic from a time before it? This idea emerges from cosmological models that propose our Big Bang was not the absolute start of time, but rather a transitional phase, a bounce from a previous contracting universe or one branch of an eternal cyclic cosmos. In such a scenario, the immense gravitational forces of a pre-existing structure, a colossal black hole or a singularity from the previous cosmic cycle, could have imprinted itself onto the newborn universe, creating a permanent scar in its initial conditions. The cold spot, in this view, would be a cosmic fossil, a fingerprint of a universe that existed before our own. It's a concept that stretches the limits of causality and questions our most fundamental assumptions about time, suggesting that the largest structures we see today might be echoes from a reality that predates time as we know it. Each of these theories, the dark matter knot, the spacetime texture, the pre-Big Bang relic, represents a heroic attempt to explain the inexplicable without leaving our home universe. They are all long shots requiring new physics or the confirmation of highly speculative ideas. Yet, that is the essence of scientific progress. When faced with a profound anomaly, we must cast a wide net, exploring every conceivable explanation from the exotic to the truly extraterrestrial. The very existence of the cold spot guarantees that our map of the cosmos is incomplete, and the quest to understand it ensures that cosmology remains one of the most dynamic and thrilling fields of human inquiry. This very question, can we even test the multiverse idea, lies at the heart of a fierce and fundamental debate within the scientific community. For an idea to be considered genuinely scientific, according to a principle famously emphasized by philosopher Karl Popper, it must be falsifiable. That is, there must be some conceivable observation or experiment that could, in principle, prove the idea wrong. If a theory is constructed in such a way that it can explain any possible outcome, then it doesn't actually make a specific prediction about the world. It becomes immune to evidence, sliding from science into the realm of pure philosophy or even pseudoscience. Critics of the multiverse argue that this is its fatal flaw. They contend that these other universes, by their very definition, exist beyond our cosmic horizon, forever outside our observational reach. Any phenomenon in our universe can be explained away by simply inventing a suitable parallel universe with the right properties, making the multiverse an untestable and therefore unscientific concept. It's a compelling argument that forces us to draw a clear line between thrilling speculation and rigorous science. However, proponents of the multiverse as a scientific framework offer a powerful counter-argument. They agree that the basic concept of an infinite multiverse is on its own notoriously difficult to falsify, but they draw a crucial distinction between the overarching multiverse theory and specific, well-defined models that emerge from it. Think of it like the theory of evolution. The broad idea that life changes over time is supported by a mountain of evidence from fossils, genetics, and observed natural selection. But within that framework, scientists make specific, testable predictions, like predicting the discovery of a transitional fossil with certain features in a specific geological layer. The bubble collision hypothesis for the cold spot operates in exactly this way. It doesn't just vaguely suggest another universe might be out there. It starts with a concrete mathematical model based on inflationary cosmology and makes a very precise quantitative prediction about our observable universe, that a collision should leave a circular cold spot with a specific temperature profile and, most importantly, a unique and detectable pattern of B-mode polarization localized to that spot. This polarization signature is the key to transforming the multiverse from a philosophical idea into a legitimate scientific hypothesis. The absence of this exact correlated signal, despite our best efforts to find it with ever more sensitive telescopes, would actively falsify this particular multiverse model. It wouldn't necessarily disprove the entire multiverse concept, but it would strongly rule out the version of it that predicts a collision with our universe. This is the essence of scientific progress, making bold predictions and allowing nature to prove you right or wrong. The search for this polarization pattern is not a vague fishing expedition. It's a targeted hunt for a specific fingerprint predicted by a specific model. This ability to make testable predictions that can be conclusively verified or refuted by empirical data is what separates scientific inquiries like the bubble collision hypothesis from non-scientific claims. It places the burden of proof squarely on the theory and gives experiment the final say. The debate ultimately reflects a dynamic tension in how science evolves. Truly revolutionary ideas often start at the very edge of testability. The concept of atoms was once a philosophical speculation by ancient Greeks, untestable for millennia until technology and methodology caught up. Similarly, the multiverse hypothesis, particularly in its detailed, predictive forms, represents a frontier of cosmology. It pushes against the limits of what we can observe, challenging us to develop new methods and technologies to explore the possibilities it unveils. The cold spot, therefore, is more than just a cosmic anomaly. It is a catalyst. It forces a critical conversation about the nature of scientific evidence and the boundaries of knowledge. Whether the final explanation is a collision with another universe, an exotic form of dark matter, or something we haven't yet conceived, the process of investigation itself is expanding our understanding of what is scientifically possible to know. The announcement of the parallel universe collision hypothesis sent ripples far beyond the quiet halls of academia, capturing the public imagination in a way few cosmological discoveries ever do. Popular science magazines and online media outlets ran with headlines that seemed ripped from science fiction, proclaiming the possibility of a bruise from another reality. This kind of story taps into a deep human fascination with the unknown, the idea that our universe might not be a lonely island but part of a vast, perhaps infinite, archipelago of worlds. It's a narrative that resonates because it's both awe-inspiring and deeply unsettling, suggesting that the very fabric of our existence might bear the marks of a long-ago encounter with something utterly alien. This public excitement is vital. It fuels curiosity, inspires the next generation of scientists, and ensures continued support for the ambitious projects that probe these mysteries. Within the astrophysics community itself, however, the reception has been far more measured and sharply divided. On one side, you have the theoretical innovators, often working at the bleeding edge of cosmology and quantum gravity. For them, the cold spot represents a thrilling opportunity. When observations stubbornly refuse to fit into the standard model, it's not a failure but an invitation to explore new physics. The bubble collision idea, for all its strangeness, is a legitimate and mathematically rigorous attempt to explain a real anomaly. These scientists argue that progress in cosmology has always required bold leaps. The very concepts of dark matter and dark energy were once considered fringe ideas proposed to explain discrepancies in observations. They see the multiverse not as science fiction, but as a natural, and in some cases inevitable, consequence of our best theories like cosmic inflation. To ignore a potential signature like the cold spot simply because the explanation sounds extraordinary would be, in their view, a failure of scientific courage. On the other side of the divide stand the more conservative, observationally driven scientists. Their skepticism is not born of a lack of imagination, but from a deep commitment to the rigorous standards of empirical proof. Their primary concern is one of falsifiability. They argue that while the collision hypothesis is fascinating, it risks becoming a theory of anything. If the predicted polarization isn't found, proponents could simply adjust the model's parameters. Maybe the collision was softer, or happened earlier, or the other universe had different properties. A theory that can be tweaked to accommodate any outcome becomes very difficult to definitively disprove. This camp advocates for exhausting every possible explanation within our own universe first. They emphasize that the history of science is also littered with anomalies that eventually yielded to conventional explanations without requiring a rewrite of reality itself. For them, the bar for evidence of a parallel universe must be astronomically high, and until that definitive, unambiguous signature is detected, extraordinary claims require extraordinary evidence that has yet to materialize. This tension between theoretical innovation and empirical proof is actually a healthy and essential engine of scientific progress. It creates a dynamic dialogue where bold ideas are constantly being stress-tested by stringent observational constraints. The skeptics force the theorists to refine their models to make more specific and testable predictions. The discovery of the cold spot's associated void, for instance, forced a refinement of the collision theory, showing how it could work in conjunction with a known underdensity rather than replacing it entirely. This back and forth ensures that science moves forward cautiously, building a consensus only when the evidence becomes overwhelming. The true resolution to the cold spot mystery won't come from one side convincing the other through argument, but from the slow, patient accumulation of data from the next generation of telescopes, data that will either reveal the smoking gun of a collision or will gradually point toward a more conventional, if still exotic, explanation within our single, wondrous universe. This intense debate, fueled by the enigmatic data from the cold spot, is precisely what drives the next great leap in our observational capabilities. The questions have been framed, the hypotheses laid out on the table, and now the race is on to gather the evidence that will finally break the stalemate. The future of this mystery, and perhaps of cosmology itself, rests on the shoulders of a new generation of telescopes and experiments, instruments of such breathtaking sensitivity that they will peer into the ancient light with a clarity we can scarcely imagine. Leading this charge are ambitious ground-based projects situated in some of the most extreme environments on Earth. High in the thin, dry air of the Atacama Desert in Chile, the Simons Observatory is nearing completion. This isn't a single telescope but a suite of instruments, a powerful array of cameras designed to map the cosmic microwave background with a resolution and sensitivity that dwarfs even the magnificent Planck satellite. Its primary mission is to hunt for the faint whisper of primordial gravitational waves by detecting their unique B-mode polarization signature across the entire sky. But its keen eyes will also be able to perform a forensic examination of specific anomalies like the cold spot. With its unprecedented ability to measure polarization, the Simons Observatory will scrutinize the spot, searching for that telltale swirl of B-modes that would point directly to a violent, primordial event like a bubble collision. If the signal is there, this observatory has a strong chance of finding it, but the quest doesn't stop there. An even more powerful successor, known as CMB-S4, is already in advanced planning stages. This project represents a monumental collaboration, combining the efforts of dozens of institutions to deploy 500,000 detectors across telescopes in Chile and at the South Pole. The scale is almost industrial, and its goal is nothing short of definitive. CMB-S4 is designed to be the ultimate CMB mapper, with a sensitivity that will allow it to either detect the primordial B-mode signal or rule it out to such a high degree of confidence that the inflationary paradigm itself would require a fundamental rethink. For the cold spot, this means an analysis so detailed that it could distinguish between the subtle polarization patterns of a collision, a gravitational lensing effect from a dark matter knot, or simply a statistical fluke. It's the equivalent of moving from a standard definition photograph to an ultra-high-resolution scan, revealing textures and details we never knew existed. While ground-based telescopes benefit from large, customizable instruments, they must peer through the blurring effects of our atmosphere. To escape this limitation, our gaze must turn back to space. The success of missions like Wilkinson Microwave Anisotropy Probe and Planck has paved the way for concepts that are even more ambitious. NASA and other space agencies are actively studying plans for a next-generation CMB satellite, often referred to as the CMB-HD mission. Imagine an observatory with resolution so sharp it could map the CMB in finer detail than Planck mapped the entire sky, but focused with laser-like precision on the large-scale anomalies. A space-based mission would be free from atmospheric interference, allowing it to measure the polarization of the cold spot with a purity and accuracy that is impossible on the ground. It could create a thermal and polarimetric fingerprint of the anomaly so detailed that we could virtually rule out entire classes of explanations, bringing us closer than ever to a conclusive answer. The technological innovation doesn't stop with simply building better cameras. A significant part of the challenge lies in the cosmic foreground, the interference from our own Milky Way galaxy. Dust, gas, and synchrotron radiation from electrons spiraling in magnetic fields all emit microwaves that contaminate the pristine signal from the CMB. To see the ancient universe clearly, we must first see through our own galactic backyard. Future missions will employ sophisticated new techniques, such as observing at many more frequency bands simultaneously. By comparing the sky at different wavelengths, powerful algorithms can effectively subtract the foreground emission, isolating the true CMB signal with far greater fidelity. This is like having a sophisticated audio filter that can remove the constant hum of a refrigerator to hear a faint, distant conversation. These advances in data processing are as crucial as the telescopes themselves, turning raw data into a clear portrait of the early cosmos. The resolution of the cold spot mystery may not come from a single eureka moment, but from a convergence of evidence gathered by these different eyes on the sky. A faint hint of a polarization pattern from the Simons Observatory, confirmed and detailed by CMB-S4, and then cross-referenced with the ultra-clean data from a future space mission. This is how a scientific consensus is built. Each new dataset will tighten the constraints, narrowing the possibilities until only the most robust explanation remains. Whether the final verdict points to a multiverse collision, an exotic form of dark matter, or a cosmic defect, the journey to get there is revolutionizing our ability to observe the universe. These telescopes are not just tools for solving one puzzle. They are gateways to a new era of precision cosmology, an era where the largest questions about our origins may finally be within our grasp to answer. The cold spot is the tantalizing target today, but the technologies developed to study it will undoubtedly reveal new anomalies, new mysteries, and new frontiers we cannot yet even conceive. But to truly appreciate the strangeness of this cosmic anomaly, we need to zoom in from the grand theoretical scale and focus our gaze on the specific patch of sky where it resides. This brings our investigation to the constellation Eridanus, the celestial river, a long, winding pattern of stars in the southern hemisphere. It is here, in this seemingly unremarkable direction, that our most powerful telescopes have pinpointed the epicenter of the mystery. While the cold spot itself is a feature of the ancient cosmic microwave background, a shadow from the universe's infancy, the region of space along our line of sight holds its own set of modern-day puzzles. As astronomers have trained their optical and radio telescopes on Eridanus, they haven't found a perfect, empty void. Instead, they've uncovered a cosmic landscape that is subtly, yet profoundly odd. The galaxy distribution is indeed sparser than average, confirming the presence of a large underdensity, but it's not a complete desert. Within this great cosmic expanse, there are isolated islands of matter, and some of these islands exhibit peculiar characteristics that have piqued the interest of researchers searching for clues. One of the most intriguing aspects of this region is the behavior of certain galaxies within the void. In a typical, dense galaxy cluster, galaxies interact frequently, often leading to bursts of star formation or dramatic transformations in their shape. But in the relative isolation of a void, galaxies are thought to evolve more quietly, like hermits undisturbed by the bustling crowds of a city. However, studies of some galaxies within the broader cold spot region have suggested they might be evolving in unusual ways. Some appear to have strangely low rates of new star formation, even for their isolated environment, as if the process of creating new suns has stalled or progressed differently. Others show morphological quirks, unexpected shapes or structures that hint at a past interaction or a unique evolutionary pathway. While none of these observations individually point to a parallel universe, they collectively paint a picture of a cosmic neighborhood that is statistically unusual. It's as if the large-scale emptiness of the region has had a tangible, and perhaps strange, influence on the individual inhabitants within it, creating a galactic environment that doesn't quite match our expectations based on other parts of the universe. Beyond the light from stars and galaxies, scientists have also listened to this region of the sky across the entire electromagnetic spectrum, searching for any other anomalous signals that could be linked to the overarching cold spot mystery. Radio telescopes, which detect long-wavelength light invisible to our eyes, are particularly powerful tools for this hunt. They can pick up the faint whispers of exotic phenomena, the synchrotron radiation from electrons spiraling at near-light speed around magnetic fields, the faint glow of cold hydrogen gas, or even the highly structured signals that might, however unlikely, indicate artificial origin. So far, no concentrated burst of radio waves, like those sometimes associated with mysterious fast radio bursts, has been definitively linked to the cold spot center in a way that suggests a connection. The region is quiet, but it's a specific kind of quiet that itself is noteworthy. Some analyses have suggested that the diffuse radio background, the faint, omnipresent radio static that fills the universe, might be slightly fainter in this direction. This would be consistent with the idea of a vast underdensity. Where there is less matter, there are fewer sources to generate this background radio fog. Yet, the measurements are at the very edge of detectability, and this remains an area of active investigation. The most compelling non-CMB signal from this direction isn't a single brilliant beacon, but rather a large-scale feature that aligns eerily well with the cold spot itself. It's known as the Eridanus supervoid, or more precisely, the Eridanus supervoid complex. This isn't a single, spherical empty bubble, but a connected series of underdense regions, a sprawling cosmic emptiness that stretches across a significant portion of the sky in the vicinity of the cold spot. The coincidence in location is striking. It strongly suggests that the two phenomena are related. The supervoid is the large-scale structure in the relatively nearby universe that lies along our line of sight to the primordial cold spot. This connection is the bedrock of the conventional explanation via the integrated Sachs-Wolf effect. But as we've discussed, the devil is in the details, and the details here are problematic. The Eridanus supervoid is large, but its gravitational influence, based on its observed depth and size, seems insufficient to explain the full magnitude of the temperature drop. This leaves scientists with a perplexing situation. The correlation between the void and the cold spot is too strong to be a simple coincidence, yet the physics we understand can't quite bridge the gap between what we see and what we need to see for a full explanation. It's like finding a suspect at the scene of a crime with a motive, but without the concrete evidence to prove they committed it. The presence of the void deepens the mystery rather than solving it, forcing us to ask whether we are missing a crucial piece of the puzzle. Perhaps the void itself is not the cause, but a secondary effect, a consequence of the same primordial event that created the cold spot, a cosmic aftershock frozen in time. So how do we test an idea that seems to stretch the very definition of science? We build a universe in a box, not a literal box, of course, but inside the humming, powerful circuits of a supercomputer. This is the domain of computational cosmology, where theorists take the complex mathematics of inflationary physics and translate them into virtual worlds. The goal is breathtakingly ambitious: to simulate the birth and potential collision of bubble universes, and to generate a precise, digital prediction of what such an event would look like on our cosmic microwave background map. It's a process that turns abstract theory into a concrete, testable hypothesis. The first step is to define the initial conditions, the starting parameters of the simulation based on our best understanding of the laws of physics. Scientists program in the fundamental rules the equations of general relativity, the properties of quantum fields, the dynamics of how a false vacuum decays to create a new bubble universe. They then set the stage for a collision by creating not one, but two bubbles within the simulated inflationary landscape. The key variables are the properties of these bubbles, their relative vacuum energies, the timing of their nucleation, and their initial distance from one another. A slight tweak to any of these parameters can result in a dramatically different collision outcome. It's like setting up a cosmic experiment with billions of possible permutations, each one telling a slightly different story of how two realities might meet. Once the simulation begins, the supercomputer crunches through mind-boggling quantities of calculations, modeling the expansion of the bubbles and their eventual collision over a timescale that, in the real world, would be a fraction of a second during the universe's infancy. The output is a detailed map, a simulated sky showing the temperature variations that would be imprinted on the CMB by the collision. The most sophisticated simulations don't just produce a simple cold spot, they predict its exact profile. They show how the temperature should drop sharply at the center of the impact zone and then gradually rise to the background level at the edges. They also predict secondary features like a subtle hot ring surrounding the cold spot or specific patterns in the way the temperature fluctuates within the anomaly itself. This level of detail is what transforms the collision hypothesis from a vague speculation into a sharp, quantitative forecast. The moment of truth arrives when scientists overlay these simulated maps onto the real-world data from the Planck satellite. This is a meticulous process of comparison, a search for a match between the digital prediction and the observed reality. Researchers don't just look for a cold patch, they analyze the cold spot's statistical properties, its sharpness, its symmetry, its internal texture, and check them against thousands of different simulation runs. The results have been both intriguing and sobering. Some early comparisons suggested that the cold spot's characteristics are rare but not impossible within the standard model of cosmology without a collision. It could, statistically, be a giant fluke. However, other, more detailed analyses have found that the cold spot's profile is statistically unusual in a way that some collision simulations can reproduce more naturally than standard explanations can. It's a delicate balancing act. The simulations have helped rule out certain types of collisions, those that would create a much more dramatic or asymmetric signature, for example. But they have also refined the theory, pointing toward a specific class of collisions that could produce a spot very much like the one we see. This iterative process, where real data shapes the virtual models and the improved models make sharper predictions, is the engine of modern cosmological discovery. It may not yet provide a definitive answer, but it is systematically narrowing the path toward one. Yet this potential discovery does more than just rewrite our cosmic address. It forces a profound philosophical confrontation with our own significance, or perhaps our lack thereof. For centuries, human thought has been anchored by the Copernican principle, the humbling realization that our world is not the center of the universe. First, we learned Earth orbits the Sun. Then we discovered our Sun is an average star in the outskirts of an ordinary galaxy, which is itself just one among billions in an expanding universe. The multiverse idea represents the ultimate and perhaps final step in this cosmic demotion. It suggests that not only is our planet and star unexceptional, and our galaxy one of countless others, but our entire universe, with its specific laws, constants, and history, might be just one page in an infinite library of physical realities. This challenges the very foundation of our search for a single, elegant theory of everything that explains why our universe is the way it is. If a multiverse exists, the laws we observe may not be fundamental, necessary truths. They could simply be the local bylaws of our cosmic neighborhood, one random outcome among a staggering number of possibilities. The deep order we perceive in nature, from the force of gravity to the mass of an electron, might not be the product of a grand design, but the result of a cosmic lottery whose winning ticket just happened to allow for our existence. This line of thinking leads us directly to one of the most debated concepts in modern cosmology and philosophy, the anthropic principle. In its simplest form, the principle observes a curious tautology. The universe we observe must be compatible with the existence of observers because we are here to observe it. It seems self-evident, almost trivial. But when placed in the context of a multiverse, it becomes a powerful and, to some, a deeply unsettling explanatory tool. Consider the remarkable fine-tuning of our universe. Physicists have identified numerous fundamental constants: the strength of gravity, the mass of the proton, the energy of the vacuum, that seem perfectly calibrated to allow for the formation of galaxies, stars, planets, and ultimately, life. Alter any of these values by even a tiny fraction, and the universe would be a sterile, lifeless void. In a single, unique universe, this apparent fine-tuning begs for an explanation. Is it the work of a creator? Is it an incredible one in a trillion coincidence? The multiverse offers a different answer. If there are an infinite, or at least an astronomically large, number of universes, each with its own randomly selected set of physical laws, then it is no longer surprising that we find ourselves in one of the rare, hospitable ones. We shouldn't be amazed to find ourselves living on a planet that has water and air. We couldn't live anywhere else. The anthropic principle, in this view, doesn't explain why our universe is fine-tuned for life. It simply states that in a vast multiverse, someone had to win the lottery, and we are the ones who did. It swaps the question of why for a statistical inevitability. This statistical reasoning opens the door to one of the most mind-bending implications of an infinite multiverse: the possibility of doppelgangers. If space is infinite and the number of possible configurations of matter is finite, then given enough room, patterns must eventually repeat. We see this on a small scale with a deck of cards. Shuffle it enough times and eventually you'll get the same sequence twice. Now, apply that logic to a cosmos of infinite size and infinite universes. Every possible event that has a non-zero probability of happening must in fact happen not just once, but an infinite number of times. This suggests that somewhere in the multiverse, there could be an Earth almost identical to ours, where a version of you is reading this very sentence, but perhaps made a slightly different choice this morning. There could be universes where the Roman Empire never fell, where dinosaurs still roam, or where the laws of physics are so alien that matter and life as we know them are impossible. The existence of such copies would fundamentally alter our understanding of identity, choice, and the meaning of a single life. Your accomplishments, your struggles, your very consciousness would not be unique, but merely one instance of a pattern replicated across the cosmos. This idea can be either terrifying or liberating, diminishing the weight of our individual choices while simultaneously connecting us to a cosmic tapestry of unimaginable breadth. However, the multiverse hypothesis is not without its fierce philosophical critics. Some argue that by invoking an infinite ensemble of unobservable universes to explain the features of our own, we are engaging in a form of intellectual surrender. It risks making cosmology untestable and unscientific. After all, if any oddity in our universe can be explained away by saying, "It just happened that way in our bubble," then we risk halting the search for deeper, more fundamental explanations that might operate within a single cosmos. Others find the anthropic principle to be a deeply unsatisfying explanation. It answers the why of our existence with a cosmic shrug, a statement that it was bound to happen somewhere, so why not here? This feels like an evasion of a profound mystery rather than its solution. Furthermore, the concept of infinite copies can lead to paradoxical conclusions. If every decision branches into a new universe, then for every version of you that achieves greatness, there is another who meets failure. This raises disturbing questions about probability and identity. Which one is the real you? The multiverse, for all its potential to solve scientific puzzles, creates a host of new philosophical ones that challenge our most basic notions of reality, causality, and our place within it. It forces us to choose between a single, special, but unexplained universe and a vast, mostly barren multiverse where we are both inevitable and insignificant. Of course, the collision hypothesis is a thrilling narrative, a story that could redefine our cosmic address. But before we pack our bags for the multiverse, we must step into the skeptic's corner, a place where scientific rigor meets a healthy dose of caution. For every theoretical physicist captivated by the possibility of parallel worlds, there is an observational cosmologist urging restraint, reminding us that the most extraordinary claims require an unassailable mountain of evidence. This perspective isn't born from a lack of imagination, but from a deep respect for the history of science itself, a history littered with beautiful, complex theories that were ultimately undone by a simpler, more mundane truth. The guiding principle for many skeptics is a centuries-old philosophical rule known as Occam's razor. In essence, it advises that when faced with competing explanations for a phenomenon, the simplest one, the one that requires the fewest new assumptions, is usually correct. When we apply this razor to the cold spot, the choice seems clear. On one side, we have the supervoid hypothesis. It requires no new physics, no rewriting of our cosmological models. It simply posits that we have found an exceptionally large, but not entirely impossible, underdensity of galaxies, and that its gravitational effect, combined with the accelerating expansion of the universe, has created the cold patch. It's an explanation that operates entirely within the well-tested framework of general relativity and the standard model of cosmology. On the other side, we have the bubble collision idea. This theory requires us to accept the existence of an entire multiverse, a mechanism for eternal inflation, the possibility of bubble nucleation, and a specific type of collision that leaves a very particular signature. The number of new, unproven assumptions is staggering. From the skeptic's viewpoint, choosing the multiverse explanation at this stage would be like hearing a strange noise in your attic and immediately concluding it's a ghost without first checking for squirrels, loose floorboards, or the wind. The responsible first step is always to exhaust every conceivable conventional possibility. This cautious approach is echoed by many prominent figures in the field. Astronomers who have dedicated their careers to mapping the large-scale structure of the universe often point to the immense challenges of galaxy surveys. They argue that our census of the cosmos is still incomplete, especially when it comes to charting the true three-dimensional shape of the largest voids. The observed Eridanus underdensity might be part of a far larger and more complex structure than our current maps can reveal. Perhaps it is not a single spherical void, but a connected network of emptiness whose combined gravitational influence is greater than we can currently calculate. The subtle effects of foreground dust and gas in our own galaxy could also be subtly contaminating the CMB measurements in that specific direction, creating an illusion of a deeper cold spot than actually exists. Until we can rule out these observational uncertainties with absolute confidence, leaping to a multiverse conclusion is, in their view, premature. The history of cosmology provides a powerful cautionary tale. Time and again, anomalies that seemed to defy explanation were later resolved without the need for revolutionary new physics. In the 1960s, the discovery of quasars, incredibly bright, distant objects, baffled scientists. Some proposed they were the exhaust vents of alien spacecraft or evidence of entirely new states of matter. The real explanation, that they are powered by supermassive black holes at the centers of galaxies, was just as profound but fit neatly within the known laws of physics. More recently, the initial measurements of the expansion rate of the universe, the Hubble constant, showed frustrating discrepancies between different methods. For a time, some theorists suggested this Hubble tension might be a sign of new particles or a flaw in our understanding of dark energy. Yet, with more precise data from missions like the Hubble Space Telescope and Gaia, the gap is slowly closing, likely pointing to subtle systematic errors in measurement rather than a crack in the cosmological model. The cold spot could very well be the next chapter in this story, an intriguing puzzle that ultimately yields to a more complete understanding of the universe we already know, rather than forcing us to invent a reality we cannot see. The most pointed criticism often comes back to the fundamental requirement of falsifiability. A theory that cannot be tested, that cannot be proven wrong, sits in a nebulous zone between science and philosophy. Skeptics argue that while the bubble collision model makes a specific prediction about B-mode polarization, the theory itself is so flexible that a negative result might not kill it. If the predicted polarization isn't found, proponents could simply adjust the model's parameters. Maybe the colliding universe had a different vacuum energy, or the collision happened at a slightly different time. A theory that can be continuously modified to avoid contradiction risks becoming unfalsifiable. This doesn't mean the multiverse idea is wrong. It means that from a strict methodological standpoint, it has not yet earned the status of a robust scientific hypothesis. The burden of proof remains squarely on those making the extraordinary claim. Until that definitive, unambiguous signature is detected, the polarization bullseye that cannot be explained by any other known process, the skeptical position is not one of denial, but of disciplined patience. It is the voice that insists we keep looking at the attic for squirrels, confident that the truth, however surprising, will ultimately be found in the data, not just in the daring reaches of our imagination. This connection between a potential multiverse collision and the fundamental forces shaping our cosmos brings us to the heart of modern cosmology's greatest enigma, dark energy. You see, the very mechanism that makes a bubble collision a plausible explanation for the cold spot is driven by the same mysterious phenomenon that is causing the universe's expansion to accelerate. Dark energy is the name we give to that repulsive force, and its nature is completely unknown. In the bubble collision scenario, the immense energy released at the boundary between universes acts as a temporary, hypercharged dose of dark energy within that specific region. It gives that patch of spacetime an extra powerful push, stretching it more rapidly than its surroundings and cooling the photons within it. This isn't a coincidence. It suggests that if the collision hypothesis is correct, we might be glimpsing a more violent, localized version of the same force that is gently accelerating the entire cosmos today. Studying the cold spot could therefore provide a unique laboratory for understanding dark energy itself. We can't recreate these extreme conditions anywhere else, but if this cosmic scar is real, it offers a fossilized record of how vacuum energy behaves under the most intense circumstances, potentially revealing clues about why our universe is evolving the way it is. The thread of this mystery pulls us back even further in time, to the universe's very first instance and the theory of cosmic inflation. This period of faster-than-light expansion is the cornerstone of our modern Big Bang theory, and it is within the framework of inflation that the multiverse concept naturally arises. The physics of inflation suggests that once it starts, it's effectively eternal, continually spawning new pocket universes like bubbles in a boiling pot. A collision between two such bubbles is not a bug in the theory. It's a feature, a predicted outcome of this chaotic process. The properties of the cold spot, its size, its temperature profile, could therefore be a direct message from the inflationary epoch. By analyzing this anomaly, we are indirectly testing the specific models of how inflation worked. Did it end smoothly in our region, or was it a more violent transition? The characteristics imprinted on the cold spot could act as a cosmic seismograph, recording the tremors of that primordial event. A collision would imply a specific kind of inflationary landscape, one where bubbles form relatively close together, constraining the vast array of possible inflationary theories and giving us a rare glimpse into the physics that operated at energies 1 trillion times higher than what we can achieve in particle colliders. This interplay between the infinitely large and the infinitesimally small is where the true profundity of the cold spot lies. The quest to explain it forces a conversation between cosmologists studying the universe on the grandest scales and particle physicists probing the fundamental rules of reality. The vacuum energy that drives cosmic acceleration and the quantum fields that would have collided in a multiverse event are ultimately described by the same theoretical frameworks. A confirmed bubble collision would provide the first observational evidence that these abstract concepts have a tangible, physical reality on cosmic scales. It would bridge a chasm in our understanding, suggesting that the laws governing the quantum world are inextricably linked to the fate and structure of the entire cosmos. The cold spot, therefore, is more than just a cold patch on a map. It is a potential keystone, a single piece of evidence that could connect the puzzle of dark energy, the theory of inflation, and the search for a unified theory of physics into one coherent picture of existence. But how do we actually measure the shape of something we can't see? This is where one of Einstein's most remarkable predictions comes into play as a powerful investigative tool: gravitational lensing. Think of space not as a static stage, but as a flexible sheet of rubber, warped and curved by the mass of any object resting upon it. A massive galaxy cluster doesn't just sit in space, it creates a deep dimple in the fabric of spacetime itself. Now, when light from a more distant object travels through this warped region, its path is bent, much like a marble rolling across a curved surface will change direction. This effect, gravitational lensing, turns massive cosmic structures into natural telescopes, magnifying and distorting the images of galaxies that lie far behind them. There are two main types of this phenomenon that are crucial for our investigation. Strong lensing creates dramatic, beautiful arcs and rings around the heaviest galaxy clusters, a clear signature of extreme warping. But for mapping the subtler, more diffuse structure of a potential supervoid, we rely on weak gravitational lensing. This is a far more delicate effect. Instead of creating obvious arcs, the gravity of a large, underdense region like a void subtly shears the shapes of the millions of background galaxies behind it, stretching them in a coherent, though almost imperceptible pattern. It's like looking at a field of distant lights through a gently warped pane of glass. Each point of light is distorted just a tiny bit, but by measuring the collective, statistical alignment of thousands of these distorted galaxies, we can reconstruct the precise shape and depth of the invisible cosmic lens, in this case the proposed Eridanus supervoid. To undertake this cosmic cartography project, astronomers use the most powerful wide-field telescopes on Earth, like the Victor M. Blanco telescope in Chile, which houses the dark energy camera. This instrument is perfectly suited for the task. It can capture incredibly detailed images of vast swaths of the sky, cataloging the shapes and positions of billions of galaxies. By analyzing the minute, systematic distortions in the shapes of galaxies that lie in and around the cold spot region, scientists can create a high-fidelity, three-dimensional mass map. They aren't just counting galaxies anymore, they are weighing the entire region, measuring the total amount of matter, both the visible stars and the invisible dark matter that resides along our line of sight. This mass map is the key to breaking the deadlock between the supervoid and collision hypotheses. If the gravitational lensing data reveals a truly colossal, deep underdensity that aligns perfectly with the cold spot, one with enough gravitational influence to account for the full temperature drop via the integrated Sachs-Wolf effect, then the mystery could be considered solved by conventional means. We would have found the missing mass, or rather, the profound lack of it that explains the anomaly. However, if the lensing maps show that the void is indeed as modest as the galaxy counts suggest, that there simply isn't enough missing matter to create such a deep, cold spot, then the case for an exotic explanation becomes dramatically stronger. This precise measurement tightens the constraints around the supervoid theory, effectively closing the door on it if the numbers don't match. It forces any remaining viable theory to explain not only the cold spot itself, but also why the observed matter distribution is so inadequate. A bubble collision, for instance, could potentially create both the temperature anomaly and influence the formation of structure in that region, leading to the observed underdensity as a secondary effect. The lensing data, therefore, doesn't just test one idea, it refines the playing field for all ideas, telling us exactly what any successful theory must account for. It transforms the mystery from a debate about possibilities into a puzzle with concrete, numerical boundaries. The ongoing analysis of this weak lensing data is a meticulous process, separating the faint signal of the void's gravity from the noise of random galaxy shapes, but the results will provide one of the most critical and objective pieces of evidence in this cosmic courtroom. What's truly remarkable about this cosmic mystery is how it has transcended the pages of astrophysics journals to become a fixture of our cultural landscape. The notion of a parallel universe leaving a tangible mark on our own is a concept so powerful that it resonates far beyond the scientific community, sparking the imagination of storytellers, filmmakers, and curious minds around the world. Documentaries have been quick to seize upon the cold spot as a prime example of science on the edge. Major series on cosmology and the universe often feature it as a climactic puzzle, with sweeping CGI visuals portraying the collision of two cosmic bubbles. These productions do more than just present the facts. They frame the investigation as a grand detective story, with scientists in the role of cosmic sleuths following a trail of clues that leads to the precipice of known reality. This storytelling transforms abstract data into a narrative of human curiosity, making the pursuit of knowledge feel as thrilling as any fictional adventure. It brings the public along for the journey, allowing everyone to ponder the same profound questions that keep cosmologists awake at night. This cultural footprint extends deeply into the realm of science fiction literature and film. The cold spot has become a go-to reference for authors seeking a scientifically plausible hook for stories about alternate realities and cosmic encounters. We see its influence in narratives where characters discover anomalies in space that serve as gateways to other dimensions or as evidence of a larger, multidimensional war. It provides a seed of real-world credibility that allows the most fantastic plots to feel grounded and eerily possible. online, the mystery has fostered vibrant communities of amateur astronomers and physics enthusiasts. Forums and social media platforms buzz with discussions where users dissect the latest research papers, share their own visualizations of the Planck data, and debate the merits of the collision hypothesis versus more conventional explanations. This democratization of discourse means that the conversation about the cold spot is no longer confined to lecture halls. It's happening in living rooms and on computer screens everywhere, with people from all walks of life contributing their perspectives and fueling a collective sense of wonder. This widespread fascination reveals something fundamental about our relationship with the cosmos. Frontier science, especially when it brushes up against concepts as mind-bending as the multiverse, acts as a catalyst for creativity. It provides a new vocabulary and a new set of icons for exploring age-old questions about our place in the grand scheme of things. The cold spot, in particular, has become a modern-day celestial Rorschach test. For some, it represents the thrilling possibility that we are not alone in the grandest sense imaginable. For others, it's a symbol of the vast, unknown mysteries that still lie beyond our understanding, a humbling reminder that for all our knowledge, the universe retains its capacity to astonish us. It fuels a sense of wonder that is essential not just for artists and writers, but for the scientific endeavor itself. The public excitement generated by such mysteries helps secure funding for the next generation of telescopes and inspires young students to pursue careers in science, technology, engineering, and mathematics, ensuring that the quest to solve these puzzles will continue for decades to come. Our journey to understand this cosmic riddle didn't begin overnight. It's a story that has unfolded over decades, a meticulous scientific detective story where each new discovery has built upon the last, gradually leading us to the edge of known physics. To truly appreciate where we are today, let's trace the timeline of this investigation, a series of pivotal moments that have shaped our current understanding. The foundation was laid in the mid-1960s, not with a grand search for cosmic origins, but with a persistent, unexplained hiss in a radio antenna. Arno Penzias and Robert Wilson, two engineers at Bell Labs, were trying to eliminate background noise for satellite communications when they stumbled upon a signal that was uniform in every direction. After ruling out everything from pigeon droppings to terrestrial interference, they realized they had found something profound, the cooled remnant of the universe's fiery birth, the cosmic microwave background. This accidental discovery, which earned them the Nobel Prize, gave us the very canvas upon which the cold spot would later be found. It was our first baby picture of the cosmos. For the next 30 years, our view of this background radiation remained relatively blurry. We knew it was there, and we knew it was remarkably uniform, but we lacked the technology to see its intricate details. That all changed at the dawn of the 21st century with the launch of NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, in 2001. This spacecraft was a game-changer. Its mission was to map the subtle temperature fluctuations in the CMB with a precision never before achieved. For years, WMAP collected data, and when its full sky map was released, it revolutionized cosmology. It confirmed the standard model of the Big Bang with incredible accuracy, pinning down the universe's age, composition, and geometry. But within this stunningly detailed map, there were subtle anomalies, features that didn't quite fit the perfect cosmic blueprint. And it was in this rich dataset that a team led by Dr. Lawrence Rudnick, analyzing the data in 2007, identified the most prominent anomaly of all, a vast, inexplicably cold region in the constellation Eridanus. The cold spot had officially entered the scientific lexicon, shifting from a statistical possibility to a concrete problem demanding an explanation. The immediate scientific response was a search for a conventional cause. The leading hypothesis, as we've discussed, was the supervoid, and astronomers began scanning that region of the sky with powerful optical telescopes. They found an underdensity of galaxies, but it was smaller than expected, creating the tension we see today. To settle the debate about the cold spot's reality, we needed an even sharper image. That came with the launch of the European Space Agency's Planck satellite in 2009. Planck was WMAP more sensitive successor, equipped with instruments capable of measuring the CMB in exquisite detail across multiple frequencies. When Planck's map was unveiled, it was a thing of beauty, a high-definition version of the universe's first light. And there, confirmed with even greater clarity, was the cold spot. It was no data glitch, it was a real feature of our universe. This confirmation, around 2013, forced the scientific community to take the anomaly seriously and truly begin entertaining more exotic explanations. It was in this fertile ground of puzzling data that the most radical idea took root. Building on the theoretical framework of eternal inflation, which naturally suggests a multiverse, physicists like Laura Mersini-Horton had already begun proposing that collisions between these bubble universes could leave observable imprints. With the cold spot now confirmed as a real and challenging feature, this hypothesis moved from pure mathematical speculation to a potential, if startling, solution. The period from around 2010 to 2015 saw a surge in theoretical papers modeling these collisions and predicting their specific signatures, directly comparing them to the Planck data. This brought the multiverse hypothesis from the fringe closer to the mainstream of cosmological discussion, setting the stage for the next phase, the direct hunt for proof. That brings us to the present day and the near future. The current era, from roughly 2018 onward, is defined by a new generation of observational campaigns. The focus has shifted from simply confirming the cold spot's existence to performing a forensic analysis on it. Scientists are now using advanced statistical techniques to analyze its exact shape and temperature profile. More importantly, the hunt is on for the smoking gun, the unique pattern of polarized light, the B modes that a collision would have created. Ground-based telescopes like the Simons Observatory in Chile are now coming online, designed with the specific sensitivity to detect this faint signal. The timeline of this mystery is now pointing toward a decisive moment. Within the next 5 to 10 years, data from these powerful new instruments will provide the evidence needed to either confirm the collision hypothesis or rule it out, potentially closing one of the most thrilling chapters in modern cosmology, or opening a door to a reality far grander than we ever imagined. So where does this leave us? After this incredible journey from the faint hiss of the cosmic microwave background to the thrilling possibility of a multiverse collision, we are left not with a final answer, but with a set of even more profound and pressing questions. The investigation is far from over. In many ways, it has just reached its most critical juncture. The biggest question hanging over all of cosmology right now is a simple one with monumental implications. Is the polarization signal there? The hunt for the unique, swirling B-mode pattern within the cold spot is the definitive test. The next generation of telescopes, like the Simons Observatory, are essentially the most sensitive polarizing filters ever built, and their primary mission is to scour this region of the sky for that specific fingerprint. Finding it would be the closest thing to a smoking gun we could hope for strong, multi-layered evidence pointing toward a violent, primordial event. But its absence would not be a dead end. It would force a dramatic re-evaluation, compelling theorists to go back to the drawing board and potentially strengthening the case for other exotic explanations, like a knot of dark matter or a cosmic defect. The answer to this single question will dictate the direction of cosmological research for decades to come. Even as we search for that polarizing signature, the case of the supervoid remains frustratingly unresolved. Can we find a better-fitting supervoid? Our current maps of the large-scale structure in the direction of Eridanus are good, but are they complete? It's entirely possible that the void we have detected is just one lobe of a far larger and more complex underdensity, a cosmic emptiness so vast and intricate that our current galaxy surveys have only glimpsed a portion of it. The ongoing weak gravitational lensing studies are crucial here. By measuring not just the number of galaxies but the total gravitational pull or lack thereof of the entire region, we will get a true measure of its mass deficit. If these new, more precise maps reveal a gravitational shadow deep enough to explain the full 70 microkelvin temperature drop through the integrated Sachs-Wolf effect, then the mystery could be solved with known physics. But if they confirm that the void is indeed as modest as it appears, then the door to more radical explanations swings open even wider. This is a question of pure observational power, and with every new sky survey, we get closer to a definitive census of the cosmic emptiness in this peculiar part of the universe. And this leads us to a broader, more statistical mystery. Are there other similar cold spots in the cosmic microwave background? Is the cold spot in Eridanus a unique cosmic unicorn, or is it merely the most prominent example of a class of anomalies? If our universe is part of a multiverse where bubble collisions are a natural occurrence, then perhaps we should expect to find more than one scar. Conversely, if it is a rare statistical fluke, a 1 in a million chance manifestation of the random quantum fluctuations from the Big Bang, then we would not expect to find another of similar size and coldness. Scientists have already scanned the rest of the Planck data, and while there are other anomalies, none match the scale and significance of the one in Eridanus. This uniqueness cuts both ways. It makes it statistically suspicious and worthy of an exotic explanation, but it also makes it harder to study through comparison. Finding a second, comparable cold spot would be a game-changer, providing a pattern for scientists to analyze and potentially revealing the mechanism that creates them. The search for other anomalies is a quiet but persistent effort in cosmology, because every strange feature on the map is a potential clue to a deeper truth hidden in the ancient light. Underlying all these specific questions is a more fundamental and philosophical uncertainty. What does the cold spot ultimately tell us about the limits of our standard model of cosmology? This model, known as the lambda cold dark matter model, has been spectacularly successful, accurately predicting a vast array of observations from the abundance of light elements to the large-scale structure of galaxies. But the cold spot, along with a few other large-scale anomalies, represents a persistent itch that the model hasn't been able to scratch. Is the lambda cold dark matter model essentially correct, with the cold spot being a minor statistical outlier? Or is this anomaly a sign of a crack in the foundation, a hint that our understanding of dark energy, dark matter, or the very initial conditions of the universe needs a significant revision? The cold spot has become a benchmark, a test case for the resilience of our core cosmological theories. How we finally explain it will determine whether our current model is merely incomplete or if it requires a fundamental overhaul, pushing us toward a new and deeper understanding of the cosmos. Ultimately, the greatest unresolved question is one of reality itself. The cold spot forces us to confront the nature of scientific evidence and the boundaries of knowledge. If the data continues to point toward a collision, we must grapple with the philosophical implications of a multiverse. If it points to an exotic form of dark matter, we must rewrite our understanding of the universe's most abundant substance. And if it remains stubbornly unexplained, it becomes a permanent reminder of the vastness of our ignorance. This is not a failure of science, but its greatest strength. The most exciting mysteries are not those we solve quickly, but those that endure, that push our technology to its limits and our imaginations to their breaking point. The cold spot is a gift to curiosity, a cosmic puzzle that guarantees the future of cosmology will be anything but dull. The answers are out there, imprinted on the oldest light in existence, waiting for the next generation of telescopes and the next brilliant insight to bring them into focus. And so our cosmic journey brings us full circle. from a faint, puzzling chill on a map of ancient light to the precipice of a reality far grander than we ever imagined. We began with the echo of the Big Bang itself, the cosmic microwave background, a relic that serves as the ultimate control for our universe. On that near-perfect canvas, we found an anomaly, the cold spot, a void of such scale and coldness that it defied simple explanation. We followed the scientific trail, first ruling out instrument error, then testing the leading idea of a supervoid, only to find that even an immense cosmic emptiness couldn't fully account for the data. This dead end forced us to consider the extraordinary, that this mark might be a scar from a collision with another universe in a vast multiverse. We explored the theoretical underpinnings, from eternal inflation to the search for a definitive polarization signature, and weighed it against other exotic possibilities. The truth is, we stand at a crossroads. The answer remains hidden, a secret locked in the faint swirls of polarized light that our most powerful telescopes are only now learning to read. But the profound value of this mystery lies not in a final answer, but in the investigation itself. The existence of the cold spot is a testament to the power of human curiosity. It pushes our technology to its limits, forces our theories to evolve, and challenges us to question the very nature of reality. It reminds us that the universe is under no obligation to be easily understood by us, and that its greatest wonders are often hidden in the details, waiting for a persistent and creative mind to uncover them. The story of the cold spot is still being written. The next chapter will be authored by the data streaming in from observatories in the high deserts of Chile and the icy plains of the South Pole. I urge you to follow along, subscribe to science news channels, read about the latest findings from projects like the Simons Observatory, and let your own imagination grapple with the possibilities. What do you think the cold spot is? A cosmic fluke, a dark matter knot, or our first glimpse of a parallel reality? The conversation is far from over, and your perspective is a part of it. Share your thoughts, your own theories on this greatest of cosmic whodunits in the comments below. The universe is asking a question. Let's see if we can find the